Hello and welcome to today's webinar presented by Dlubal software. Today we'll be working in our finite element analysis and design software, Rfem. The title for today's webinar is Piping Design per ASME in Rfem. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Stefan Frenzel will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the webinar content for the next hour today, we want to go through a piping system example in Rfem and also utilizing our RF piping extension module. So here we'll be modeling our piping system on a supporting structure. We're going to further define components such as reducers, valves, branch connections, and a few more. We're going to define load cases and apply loads to these piping members. And we will also automatically generate these load combinations according to the ASME standard. Now furthermore, we're going to utilize the RF piping design module. This will give us our utilization ratio, our stress checks according to the ASME B31.1 or B31.3. Lastly, I want to touch on the overview of the supporting structure design. This will allow us to design of steel per AISC, for example, or ACI with some additional design modules. With that said, we can jump into our Rfem model. So we have here the supporting structure. For the sake of time, I already have this modeled. This was done completely in our main program here, Rfem. If I zoom in here, I've also added some rigid links to the top of my W shapes. And you'll notice that with these rigid links, if I double click on them, this is where our piping members are going to frame into the supporting structure. What I did was add in a member hinge to the rigid link here to release translation in the global X direction. So that will allow those pipes to kind of slide back and forth in that direction. I also released the moment. So I didn't want any moment transfer between our piping members and the supporting structure, so we can do so with the member hinge on our rigid links. Now, taking a look at the rest of the structure, these are just typical W shapes. We can use our project navigator over here on the left to view all of the input data. So for example, the cross sections tree, we can see that the W8x35s are defined for most of our members within this pipe rack. We also have some diagonal vertical bracing, W4x13s. So that's really all that I've done so far. Now, when you go to create a new model within Rfem, or after you've done, such as I have, created the model, we need to go back into the general data. So what we would do is to right-click on our model name, go into the general data, and under the options tab, you'll notice piping analysis. So this option is only available if you've purchased the RF piping module extension. So here we will check this checkbox, and under the details are some additional settings that we need to define. The first one is to define which standard we like to use. We have the ASME B31.1, 31.3, and recently added is the Euro code. This option down below at this checkbox is for welded forged T and welded in contour inserts. This just refers to a couple variables, RX and TC, that we won't be using today, but just keep that in mind if you are using those type of components. The default branch connection type, this will make a little bit more sense later on. So for right now, we just want to set this to reinforced fabricated T, but just keep in mind that this setting is here and I'll mention it later on. Generated combinations. If we have this option checked, this will automatically create the load combinations according to the ASME standard. Now, underneath this setting are two different options. We have either result combinations or piping load combinations. Now, these are for expansion combinations. For now, I'm going to select the solve independently with piping load combinations. This is something else that I'll get into later on that'll make much more sense. Just keep in mind that result combinations, you cannot utilize nonlinearities. So material nonlinearities or geometric nonlinearities cannot accurately be taken into account with a result combination. That's one reason why we'll move forward today with solving independently with load combinations only. We can also incorporate hydrotest loads into our generated load combinations if we had the need for that. Under the internal pressure, we do want to take into account displacements due to pressure from the Bourdon effect. For this, we can account for elongation and straightening, which is what we'll choose today. Now, the Bourdon effect can be treated either as expansion loads or sustained loads, and this is important for our load combination generation as well as the specific stress checks that we'll be doing according to the ASME later on. Material properties. This is automatically checked. So this uses temperature-dependent material properties. What's happening here, which we'll see when we define our material, is that actually as our materials are changing temperature, we can also change the stiffness of the materials. This is a material nonlinearity. So things like the modulus of elasticity will be dependent on the particular temperature within that material of our piping system. So very, very powerful in terms of material nonlinearities. So when I click OK out of these dialog boxes, you'll notice that I'm still within RFEM, but now I have some additional tools available to me for modeling piping systems. So we want to begin with today by drawing a new pipeline. So that's this first tool available in our new toolbar. For the pipeline description, we'll call this one main pipe 1, and we need to define a cross section. So with the cross-section, we will go into our database and up pop several different manufacturers, standards. Now you'll notice that we have the ASME B31.1. We have NPS and DN. NPS is going to be related to imperial units. DN is going to be related to metric. For our first pipe, I want to scroll down here to my 8-inch diameter, and in particular 8.625, and the thickness of the wall is going to be 0.594. So I can see my cross-section populated here. If I have any questions about what variables are being used for my cross-section properties, I can open up this info box to see everything listed here. The material is also going to be defined within the same dialog box. So here we will open up our material database. Then over on the left we have some filters where we can filter down to the ASME B31.1. So these are all the materials listed in Appendix A within the ASME standard, which you can see it's quite complete. For today, we will just stick with the A53 grade A, and then here are all my material properties. So this is what I had mentioned previously, that as our temperatures are changing, so are our dependent properties such as modulus of elasticity, thermal expansion, allowable stress. So these will actually change with each iteration as long as the temperature continues to change as well. Now that we have fully defined our cross-section, our material, both of those are listed in that dialog box that we were previously in. Now the line mass here is nothing more than just the density of our material multiplied by the cross-sectional area of our pipe to give us our mass per unit length. The total line mass is correlated here just with the line mass that we've defined so far, but you'll see this begins to change as we define some additional parameters with these other tabs up here at the top. Design data. This is important because it is going to relate to our pipe wall thickness checks and pressure checks according to the ASME later on. So we want to initially give some design data here that we plan to design this pipe to. So for example, if we plan to use a pressure no greater than 500 psi, and maybe we plan to design around 85 degrees Fahrenheit, nothing too hot or extreme here. The second tab is the bend. You actually can create a different cross-section of the bend of the pipeline different from the straight pipe. This is important for things like thermal temperatures. They create much higher stresses at bend. So if we wanted to maybe change this cross-section to a thicker wall, we can do so. The rest of these parameters line up just to what we saw in the straight pipe tab. Layers. We can include layers such as insulation, plating, and lining. For today, we'll stick with applying an insulation. And what we'd want to do here is to define the weight of the insulation as 6.37 pounds per cubic foot, and as well as the thickness. So we'll add 2 inches of insulation to the inside of this particular cross section. We'll also add some plating. For this, the specific weight needs to be quite a bit higher at 497.2, just something that we're given from the manufacturer, and a thickness of 0.04 inches. Now you'll start to see this total line mass increase from what we saw with the first tab because we're accounting for the additional weight from the insulation and the plating. Stress analysis parameters, well, here you can see there's corrosion allowances, mill tolerances, manufacturing allowances, and welding factors. Again, this is important for when we're checking the pipe wall thickness checks according to the ASME. There are some default settings in here, but by all means, you have control to override those for both the straight pipe and the bend. Now I can click OK, so we're back to our original dialog box. So we define all the properties for our cross section. Now you'll also notice that we have bend available here. What this means is that as I begin to draw my pipeline back here in RFEM, I can actually automatically create the geometry for the bends. So right now we have it set to the long radius. The bend radius is set to 12 inches. We can change this to short and use 8 inches, or we can choose a user-defined radius here. The bend factors, these are calculated from the ASME. The flexibility factor has influence on the bending stiffness of the pipe bend. The stress intensification factor is something that will be used for design later on in our add-on module RF piping design. Again, you can override these with user defined as well. So now that we have defined everything for our first piping member, what we want to do is to begin drawing it. And you'll notice I have these crosshairs available in my graphical interface. What I'd like to do initially is to change the drawing grid around a little bit. So I'm first going to change the plane, and then I can easily select a different origin here. And I'm going to snap to the top of this rigid link here. So when I go to draw a pipeline, I have a few options. I can choose the current coordinate system, which is what I'm going to do. That will just leave this grid as it is. I can also choose a grid origin or the last node. The last node will dynamically change according to the clicks I make in my model as I begin to draw this pipeline. So to begin with, we will start in an elevation view here, and I'd like to choose a point -2570. So I make my first click, and then I go to a point about a foot away from the face of the supporting structure. Now you'll notice that as I move vertically up my supporting structure, the bend is automatically accounted for. So that's what the bend option does. We can see that right to the left of the supporting structure. So we go all the way up to the top, and we can begin drawing the pipe across the top of the supporting structure. Now, keep in mind that this drawing grid keeps me in one plane, so I don't have to worry about flying off into space anywhere. Now, when we get to this point over here, what I'd like to take into account is maybe some additional bends to dissipate my heat from my temperature loads. So all while I'm still drawing this same pipeline, I can change my drawing grid back to the XY plane. Maybe I snap back to the bottom of my supporting structure. Then I can zoom in and continue modeling my pipeline here with some additional bends. So once we are done with this, I will make my last final click here, and we'll snap to a point and right click to finish it. And now my piping is complete. So you can see that if everything goes well, you should have the name of your pipe here called main pipe 1. That's the description that we gave it. Now I want to create an adjacent pipe right next to it, and utilizing some of the features within RFEM to make our life a little bit easier, what I'm going to do is to turn this into a wireframe display model. Now I'm going to highlight my important nodes here, the nodes that where the bends occur, by holding down my control key and selecting all of these main nodes where the pipe makes some bends. So once I have these selected, what I can do is to use my Move Copy tool. I'll create one copy, and I'm going to move it -4 feet in the global Y direction. So I click OK. So now you'll see those copied nodes are available here. Nothing too special. So what I'm going to do is to create a new pipeline. Once again, this time we'll call it Main Pipe 2. Now the cross section, I've already defined that 8-inch diameter pipe with all the insulation, the plating. That's now available for all my pipelines to use in this particular model. So I want to use that same cross section, so I don't need to redefine anything. I'll use the same bend as well, and I can click OK. So the reason that I created those nodes now is that I can easily just snap to those nodes here without having to change around my work plane like what I did previously. So again, just using some of those special features that we have in RFEM to make modeling a little bit quicker, and I right-click to make my last point. Now, if I turn this back into rendered view, let's say, oh, okay, well, this pipe really would like to extend out a little bit further than what I have shown. Well, instead of redrawing everything, what I can do is to take this node and to simply drag and drop it so that it's adjacent to my main pipe 1. And again, everything went well. We see the name of main pipe 2 here. Now, the pipes are kind of blending into the rest of the structure. Don't really tell what's going on here. Well, under the Display tab in the Project Navigator, this controls everything that we view graphically, whether that's input data, our results we'll see a little bit later on. But if I scroll all the way to the bottom, I have this option here to change my colors and my graphic according to, right now it's just set to the standard. We can choose material, cross-section, but we also have pipelines. So when I choose that option, my panel pops up and shows me exactly what my main pipe 1 and main pipe 2 are with different colors. So sets it apart from the rest of the supporting structure. Okay, so what I'd like to continue to do is to draw in a couple of straight pipe members, just short segments that frame into this main pipe 1 so we have some intersections. I'm going to go back to the new pipeline. We'll just call this one pipe 1. And I want to define a new cross-section here. So up pops our cross-section database. Now, you'll notice that, of course, we can go back in and filter through this long list. We also can create a favorites group. By activating my favorites group, I've edited it so that I've just added the 2 cross-sections that I'm using in today's webinar. But you can imagine that if you use a handful of cross-sections quite often, this is a great way to just quickly select them. So for this one, I'll choose the 6-inch diameter pipe. We have a wall thickness of 0.31. My material is remembered from my last cross-section. We don't need to make any changes with that. I click OK. Now, as far as the rest of these tabs, bend, layers, I'm going to keep everything just as default. I'm not going to add any insulation to this. I will set the design pressure here to 585 degrees Fahrenheit and click OK. So I click OK once more, and I think easiest is to change this to my current coordinate system and to change this to wireframe view. So that way I can zoom in here, and my first point I'd like to choose is -1570. And then all I need to do is snap to a point which extends out. I right click. That's my first pipe. Creating once more a new pipeline. We'll call this one pipe 2. I've defined that smaller section, so I always have that available in this particular model. I click OK. And then I can, again, change this to current coordinate system. That's what I prefer to work with. Here we'll choose -870 and snap to a point out here, right click. Showing the rendered view, we now see those additional pipe sections shown here, and everything is colored differently so we can tell it apart. Okay, so now that I have modeled my pipelines, let's move on to the piping components. That was where the rest of these tools will come into play. So the first thing that we want to define is a new reducer. So when I click on new reducer, the program requires me to click on the pipe that I'm going to apply this reducer to. So I click on this first pipe section here. Now reducers are used to transition from a larger pipe to a smaller pipe, or vice versa. So within this dialog box, the first thing that I need to define is which dimension to change, so towards which node. This is actually opposite of what I want to do right now. So what I'm going to do is click on my beginning node here. Now you'll notice that my reducer start, perhaps I can choose that smaller cross section that we've already defined, or you can create a new section. The reducer end is grayed out because this is going to transition into the pipe I already have defined. What I do need to define is where this reducer starts. So we'll start at about 48 inches from the start, and you'll notice this big red arrow pops up exactly on the pipe of where we're going to apply this reducer. The length can also be applied at 12 inches. Well, there's our second red arrow showing us where the reducer end is. You can also define an eccentricity here. Eccentricity would be useful if you want the bottom of the pipes to be flush. In our case, it doesn't matter, so we'll keep this as is. Again, the reducer factors can be overwritten here if you'd like to do so. Now, for a lot of these components, we do have a library. Unfortunately for these library, this is more relevant to Eurocodes and European manufacturers. This is something that we do plan to implement some US manufacturers in the near future, but for now it's easy enough just to set this as user defined. For flanges, this is where maybe we would weld flanges to our pipe and we bolt them together at this reducer location. Now, I'm not going to apply flanges, but we'll do this plenty more times with other components today, so that will be more clear in just a minute. And I click OK. Now, if we zoom in, we can automatically see that reducer applied here with the smaller pipe section on the left. Moving on down our list here, we have three options for valves. So we have a two-way valve, a three-way valve, and a four-way valve. And pretty self-explanatory. Two-way valve is going to be used for two pipes connecting together. A three-way valve would be an intersection of three pipes, and a four-way valve of four pipes. So starting off with our new valve, just two-way, we're going to move to the other side of our model, and in particular main pipe 2, we're going to select this pipe here. So up pops our dialog box for a new valve. Now again, we just want to specify where this begins, so we'll start at 12 inches from the member start, indicated by my red arrow here. The length will be 12 inches, and we have some parameters here that are automatically created, such as the multiplier of the insulation mass is set to 1.75. The multiplier of thickness is set to 3. So you can override those. That ultimately affects our mass here, or you can set a user-defined mass as well. The flanges. So this is where maybe I do want to apply some flanges. We're going to plan to weld those flanges to both the valve and the pipes and bolt them together. Well, for our flanges, we want to check the checkbox that those are both available. Our nodes are automatically generated here of where that flange is going to occur. And we can simply define the mass here of our flange as 16 pounds, and maybe the nominal pressure is 232. Again, this is just information that we would get from a manufacturer. What's also nice is that I don't have to re-enter this information here, but yet I can just set to all. This will automatically populate the same flange settings for my other node. Now, additional mass tab here is useful for our hand wheel if we have an additional mass that we'd like to take into consideration, as well as the eccentricity away from the original flange. So something to keep in mind there. Now, once I click OK, then we can see here that flange is automatically created visually here and will be taken into account for stiffness, for analysis, and for design. So that makes sense for our two-way flange. Now, in a similar sense, we will apply a three-way flange. So for a three-way flange, instead of selecting a pipe, we have to select an intersection. So I select this first intersection here where we have pipe 1 framing into main pipe 1. The cross sections are automatically generated according to what we have modeled in Rfem, and we want to give it a length for all three piping components here, 12 inches. Again, our red X indicates where that occurs. Parameters, same thing that we saw within the two-way valve. We have a multiplier of insulation mass, multiplier of thickness. Our flanges here, we do want to create flanges at all locations. Again, this will be 16 pounds, 232 psi. Now, if I try and set this to all, you'll notice that nothing happens for my other two flange entries. The reason why is because we have a different cross-section defined here. The program will only automatically assign the flanges to the same cross sections. So if I move over to my 8-inch diameter pipe and I type in 16 pounds and 232 psi, and I click equals, that will set the flange for the third node automatically. And again, the additional mass can be considered with the hand wheel here. So once I click OK, then we should see that three-way valve generated graphically. So that's what a three-way intersection would look like. Now, four-way intersection, same concept. We don't have any intersections of 4 pipes here, so we won't be applying that today. Right next to that is the new bend. A new bend is useful had I not created to automatically create the bends when I drew in my pipeline. So perhaps these two elements here, these two pipes connected at a 90-degree angle, and I wanted to go back in afterwards to create that bend. You can always do so with the bend tool up here, define the radius, define a different cross section if you'd like as well. Next to that is a new flange. So this has nothing to do with some of these other components, but you can purely apply just a flange to any segment of a pipe. This might be useful if you have 2 extremely long pipes and you would like to add in a break there and they're bolted together with a flange. You can do so by adding in that flange. We also have a new blind flange. This would be able to lock nozzles and piping ends. So for example, we could add a blind flange here at one of our piping ends. A new T. So a new T would be an intersection of 3 pipes, such as what we see here with our pipe number 2. Nothing too fancy with this. We have the cross section defined with the run. The program automatically assumes that's our 8-inch pipe, and the branch is going to be the smaller 6-inch pipe. Then we just simply define the geometry, and again, we can add flanges here. For our case, instead of doing this, I'm actually going to apply a new branch connection. So again, I click this intersection. Now with the branch connection, remember back in the general data, I said that we had to set a default option for the connection type. Well, that's where this comes into play. So we set the reinforced fabricated T so that automatically when I jump into this dialog box, this is what will always be automated. Now, if I use something else quite often, then you probably want to go back to the general data and change that default value. You can always come in and individually select them as well. So for us, we're going to choose a reinforced fabricated T. All of our cross-section dimensions and factors are automatically calculated here, but what we do need to define is the thickness of our reinforcing pad or saddle thickness. So this is important to just give the pipes some additional reinforcement here or thickness at maybe where we have some high stress locations. For today, maybe we put in here a 1/4 inch thick saddle thickness and weld that directly to our pipes. Once that's done, I click OK. Now this is indicated graphically with just a ball at that intersection. As far as the other 2 options here for axial expansion joints and angular expansion joints, I will get into that later after we do design. So for now, we'll continue to move on. So before we can start loading our structure, we need to support it. Just like we support our before we begin loading our piping members, we need to support them. So just like we supported our supporting structure here, you can see at the bottom of the columns we have nodal supports. We have to do the exact same thing to our pipe elements. So we don't have any additional features for supporting the pipes. It's just what you would use in RFEM for all the rest of your members as well. So in our case, we want to create a new nodal support. Now with a nodal support, we have 6 degrees of freedom, 3 degrees in translation, 3 degrees in rotation that we can fully fix or fully release. We also have a spring constant here. So if you have something that's not fully fixed, not fully released, but somewhere in the middle, you can define a spring constant and you'll have partial fixity. Lastly, we can define nonlinearities. I don't think it's completely uncommon that maybe for a piping support, you have some type of friction support. So it's dependent on your normal forces. You can define all that with the nonlinear capabilities within the program. I'll repeat this again, but the nonlinear supports is something that cannot be taken into account with result combination. So just keep that in our heads, but we'll revisit that later. So for today, we want to use just a typical hinge type applications, one of the default options within the program. I click OK. So what I'm going to do here is just simply click at the ends of my pipes to support those with that basic nodal support. In a similar concept, going back to my nodal supports, I'd like to define a new definition. And this time I want to fully release it in the X direction, so some type of roller support that allows translation in the global X direction. I can click OK, I click OK. So now for this type of support, I'm going to turn this into wireframe view, and I'm going to zoom in here. And these will want to be applied right at the bends of the pipes. Now I'm not applying it at this node, which kind of indicates how our bend or where our bend occurs, because this node doesn't technically lie on the piping member. We need to apply it directly on the pipe. So for this, I'm just going to highlight these nodes right at the bends on both sides. And once we've completed on the right side of the structure, we'll zoom in to do this on the left side. Now, once more going back into the nodal support, because I've defined these new nodal supports, I can always select them within my drop-down box here, but I want to create one more definition, and we're going to release this in the global Y direction. So this will allow movement in the global Y as a roller support. I click OK, and that's where we want to maybe apply this to our pipes up here where we added in these additional bends. Okay, so now our structure, including our pipes, are fully supported. What I'd like to move on now is loading of the member. So for this, we want to create some additional load cases. So for this, I go to add a new load case, and up pops my load cases and combinations dialog box. Now, for those of us who are familiar with RFEM or just structural design in general, we of course have action categories according to the ASCE 7 or the NBC, according to live load, dead load, wind load, and so forth. But when you have the RF piping module activated, you'll notice that we have several more action categories available here for our piping load combinations, such as piping self-weight, we have fluid, we have pressure, snow, wind, even cold springing, hanger, hot loads, and cold loads. So for our first load case, we will define a pipe self-weight. We'll give it the name pipe self-weight. The self-weight will be activated here with this checkbox as -1 in the global Z direction. Now we create a new load case. We uncheck the self-weight because we don't want to account for that twice. This one will be for fluid, and we'll call this one pipe fluid. We create another load case. This time we will name this one temperature 1 and assign the appropriate action category. I can make a copy of these as well. So now all I need to do is to redefine temp 1 to temp 2, creating another load case such as pressure, and we'll call this one pressure 1. Making a copy, we'll call this one pressure 2. So now all of our load cases are complete. I've applied no loads, but I've just defined the load cases that eventually those applied loads will fit into. So now I want to take a look at my piping load combination. So when I try and click another tab, I automatically get this RFEM question. It tells me the load cases were changed. Not all internal pressure load cases have been assigned to corresponding thermal load cases. Do I want to do this now? Yes, I do. So now up pops an additional dialog box, which just simply assigns my temperature load cases to my pressure load cases. Now the program makes some assumptions here, but if I don't like these assumptions, I can always use my drop down to make changes, or I can add in some different combinations here. So that's important for our load combinations. Under the piping load combinations, we see some automatically generated load combinations, such as for sustained, for operating, and for expansion. So these are the various stress types, and they are incredibly important because this tells the program, once we get into design a little bit later on, exactly what load combinations to use in each of the particular sections of the ASME code for our stress checks. Now, had I chosen to create these load combinations manually, I still need to assign a stress type. Again, it's important for our ASME code design later on. When we take a look at the sustained, take a look at self-weight, pipe fluid, pressure, maybe no content weight is just the self-weight. We also have the operating, which is going to be all 4 load cases acting at once. Now we get into the expansion load cases, and this is something that is very important and relies on our settings and our general data. So remember how I said, well, we're not going to create result combinations, but rather we're going to create only load combinations. Well, this has to do with these expansion loads. So when I take a look at these expansion loads, they are nothing more than just the temperature loads applied. So then I'll be doing my expansion stress checks within the ASME according to just simply this temperature load applied. Well, in turn, what I'd like to show you is if we go back to the General Data tab, under the data, we scroll up to our name, we right-click under General Data to go right back into where we started. Here, I'm going to quickly change this to result combination. Now remember, material nonlinearities cannot be taken into account accurately, so you'd probably want to uncheck this if we're using result combinations. And I can click OK. So going back into my load cases and combinations, looking at my piping load combinations, you'll notice my expansion loads are now gone. Those load combinations are not being generated here, but rather they're now under the result combinations. So how is this different? Well, it's still called the same expansion 1, 2, and 3. But now when I look at the details of this, what's happening here is I'm taking my load combination PC5, which is my operating 1 load. I am subtracting out, indicated by this -1 sign, PC1, which is my load combination for traditional sustained. So to make this a little bit more clear about what's going on, let's go back to our piping load combination. So we're taking PC5, which is all 4 load cases applied at once. We're going to get the stresses and everything from this. Then what we're going to do is we're going to subtract out the internal forces and in turn the stresses that are generated from this traditional sustained, which you'll see is all 3 load cases, but temperature is not included. So all we're left with is just the stress generated from the temperature. Now this result combination makes a whole lot more sense than what we saw previously under piping load combinations. The reason for that is because we're probably not, actually we'll never have the temperature applied alone. Of course, there's got to be self-weight, there's got to be fluid running through the pipe, and so forth. So that's why this makes a whole lot more sense. But there's the downside that material nonlinearities cannot be taken into account, as well as geometric nonlinearities. So when I mention things like the nodal support with friction or sliding, that's a geometric nonlinearity. You'll get a warning message for your result combinations, and they cannot be taken into account accurately. So just something to keep in mind, it's kind of either or. So for today, what I'm going to do is to go back into my general data. I'm going to change this back to solving independently because I am using my temperature dependent material properties. Okay, so now that we have these load cases defined, you'll find those in our drop-down box available up here in our toolbar. We want to begin loading the pipes. So we'll start off, pipe self-weight, we'll just leave this as is. We won't apply any additional loads. Now the piping fluid. What I'd like to do is to select all my members to apply the piping fluid to. Now right now it's kind of confusing with my supporting structure. Under the Views tab, we have some generated views that as we began to model, the program generates these. And one of those options is the pipelines tree here. So what I can do is I can check this checkbox, and now my supporting structure, I can no longer select it. It's not visible. What I can do is make changes and select all of my pipelines. So that's kind of a useful feature, this Views tab, if you're looking to highlight various options within your model. So I'm going to highlight all of my members here, and I'm going to apply a new member load. So member load's exactly what you think of it. We can apply a force along a member, but for this particular application today for our pipes, we want to go under the extra. And under extra, we have the option for pipe content full. For pipe content full, we're assuming that the pipe has all of the fluid contained fully in this pipe. It's completely full, and all we need to do is to give it a specific weight. Now the other option we have is pipe content partial. This is nice because if we know that our pipe is only going to be partially filled, all we have to do is specify this distance D in inches, for example. We give the specific weight, the program will automatically calculate for us the internal force based on only having this fluid partially filled within the pipe. For today, we'll assume it's completely full. We'll assume that maybe water is being applied through these particular pipes, so a specific weight of -62.4 pounds per cubic foot. and I click OK. So now visually I can see this load being applied to all of my members here. Now I changed my load case up at the top to temperature. My members are still highlighted, so we will go back into our new member load here, and we will now apply a temperature. Here we just specify perhaps 65 degrees Fahrenheit. Nothing too special. I click OK. Graphically though, we can see this temperature load applied to all of our pipes. Moving on to temperature 2, same concept. All I'm going to do, program remembers my settings from last time, is change this to 85 degrees. Again, nothing too extreme with our temperatures for this example today. Pressure, again, member load. Under the extra, we have the option for pipe internal pressure. So here you can see an outward force will be acting from the interior of our pipe, and we again just need to simply define a magnitude. So this first pressure will be 145 psi. I click OK. Just like what we saw before, I can now see that 145 psi applied to all of my members. Lastly, one more load for pressure 2, just changing the magnitude here to 218 psi, and I click OK. So now these loads are done, but what's nice is that not only can I scroll through my load cases, but maybe I'd like to take a look at some of my load combinations. For example, operating. This is with all 4 load cases acting at once. So I can see those loads stacked on top of one another and exactly how they're going to be applied visually to my particular members. Okay, so now we're ready to run a design for the ASME. We've fully loaded this structure. We fully supported it. We've added in all of our piping components. Everything looks to be good. So now what we'd like to move on to is back under our Data tab. You can see here is our long list of add-on modules, and in particular we would like to be in the RF piping design. Now any one of these modules you can right click and choose it to be your favorite to move it up to the top of the list. So we're going to launch RF piping design, design of piping. Now this is just a simple dialog box. Those of us familiar with RFEM, this module looks like all the rest of them. So what we would like to first define here is the pipelines to design. So I can simply select my all checkbox. So now we'll design pipes 1 through 4. Now the standard can also be selected not here but back in the general data tab. So this is a little bit different than some of our add-on modules. That standard has to be generated within the general data. We did select B31.1. I'm going to move all of my load combinations to be considered for piping design. So you can see here my sustain and my expansion loads are going to be utilized appropriately within the ASME. Now moving on down the list, I have my materials. This is my A53 brought in from RFEM. I don't have to redefine that. What's further defined though are just some of those material properties if I'm curious to see those again. Cross-section, same concept. Those are brought in directly from RFEM. I don't need to do anything further with these here. Here are my cross-section properties given to me again. Now, you'll notice that I actually have results available even before I've run a calculation within the program. So this is checking our wall thickness and our pressure, doing a couple checks from the ASME. All again without running a calculation. So how is this possible? Well, for this, I want to actually jump back to the PowerPoint. And this section within our RFEM add-on module is called Internal Pressure Analysis. It refers to the ASME B31.1, section 104.1.4. This allows us to check the minimum wall thickness for pressure and temperature. So that's what these equations are given within the standard, equations 11 and 12 at this section. Now there's 2 equations here. So we have some variables that we're looking at. Now the first variable, P, is going to be referred back. Remember when we created our cross-section and I said, well, let's give a design pressure here. So this is what I'm telling the program, okay, I plan to design this pipe for 500 psi or less. That value, this design pressure, is going to be utilized within these equations, P. Now we also have some other variables, capital D sub naught, that's going to be our outer diameter, and then we have smaller d, which is going to be interior diameter. So that's why there's 2 separate equations here. We also have SE, which just refers to the max allowable stress based on our material for our particular pipe. We have a couple other variables, W and Y, which is the weld strength reduction factor and the coefficient directly from the standard. Both of those are dependent on temperature. So again, this is why we defined a design temperature, because these coefficients may change as well as some other parameters depending on what our design temperature is. Now A is going to be additional thickness requirements. That refers back to corrosion, to threading, to mill tolerances. So then we'll add in here any additional requirements to finally give you a minimum thickness that must be met for that particular cross section. The code right below this gives a couple other equations for max design pressure. Now, this is absolutely no different than these equations here. They're just manipulated so that we're solving for P. And the reason for this is that maybe we have an existing cross-section, or maybe we're absolutely confined to use one particular cross-section with one particular pipe wall thickness. Well, now we can put in that set thickness into these equations, and now we have a max design pressure. So we cannot exceed this max design pressure, which will double check that to what you have entered in here for your cross-section parameters. So those checks are kind of going on here within Rfem, our add-on module, before even running the calculation. You'll notice here I have both my 8-inch section and my 6-inch section. We will check it for both the straight pipe and the bends, because there are different checks for bends as well. We give you the code references. So here you can see the wall thickness check. We have a ratio for that. We also have our design pressure check. So we will check both of them for you before running that calculation. Now, before moving forward with the rest of these stress checks, I want to visit the details button here, which brings up our additional detail settings. So most of this is just some further details that we specify according to the ASME, such as the number of thermal cycles. Now, we always give a code reference here, so you can quickly look that up in the ASME B31.1 to understand, well, what exactly am I setting here? The occasional load factor K, you can see here we have some different settings. 1.15 is going to be used for loads acting for less than 8 hours and less than 800 hours per year. 1.2 would be used for less than 1 hour and less than 80 hours a year, and 1.0 would be the most conservative. We use 1.15. Corrosion allowances, we have two options with this. So those corrosion, mill, mechanical allowances can either be applied to the stress calculations according to the standard, so whatever the ASME tells us to apply it to, or to all stress calculations, which, as the program tells us here, this is a more conservative approach. Couple more stress options. Again, we can just refer directly to the standard to take a look at these. We'll leave them as default. Something recently added is hoop stress, calculated using either the inner diameter, but you can see that we also have the drop-down box to use the mean diameter or outer diameter. We'll just leave this as inner diameter. Okay, so now that we have defined those details, we can now move forward with our calculation to see if everything will hopefully work okay this time. Again, running through both load cases and combinations, and we should be seeing results here, and yes, we do. Okay, so now we get our results available a little bit more extensive than what we saw before. So we can view the design by load combination. So here's our sustained, here's our expansion. We can view design by cross-section. Here's our 8-inch, here's our 6-inch pipe. Design by pipeline, we should have 4 different pipelines here. We can view design by each individual member if we'd like to, or even design by X location for a very long list and detail of what's going on. Maybe moving back to my design by member, you'll notice that as I scroll through this table, if I drag it down here, in the background, the Rfem graphics are synced up to my table. So I can see exactly what stress check I'm looking at. Now, even further, this big red arrow is going to show you exactly where the controlling internal force for that particular stress is located. So, you know, maybe in our model today, not so helpful, but you can imagine with a very large model, this will be extremely helpful if you're looking at this big giant table and you want to just get an idea of where you're at within your structure. We also have parts list by pipeline material takeoff. So when we go back to design by load combination, you'll notice here we have some red numbers, and I have a big red sad face because I am above 1.0. So there's obviously something I need to address in terms of my temperature stresses and the stress checks that are related to the code. So the tables are nice, but I'd like to move into the graphics back in RFEM to see exactly where this is occurring. Well, we can choose the graphics button here. Now, when I go back into RFEM, I'm technically still in this add-on module. I'm just viewing the results graphically back in RFEM, and you can see this with our drop-down box here. So right now I'm showing the design ratios along the pipe members. Now I can't really see what's going on, but remember under the display tab I mentioned to you that everything that we view here graphically is controlled within our display project navigator. Even the results. So under the results tree here and for members, I can actually change this to a few different options, but one of them being cross sections. So now I have colored cross sections that I can kind of scroll along the pipes and to see exactly where my problem occurs. Well, it looks like these two bends here are a big problem when it comes to our temperature loads and stress designs. So I need to do something with regards to that. Well, that's where I mentioned that we would go back into an expansion joint. So although I'm still technically in this piping module, I'm just viewing my results, I can still make changes in RFEM because I'm still concurrently in RFEM. So what we're going to do is to add a new expansion joint. I just need to select the pipe I'd like to apply it to. Now for this, it looks like the other dialog boxes that we saw with our components. So here is where we're going to add in a distance, or actually we'll start off with the start location. We'll start this off 12 inches from the pipe start, so indicated by that red X once more. Now the length will be 12 inches as well. The outer diameter of my expansion joint, just some geometric properties that we need to define. The outer diameter will be 10 inches. The corrugated length, and by the way, all of this is given in this nice little picture here, so I don't have to guess what variables I'm putting in, but the corrugated length will be 10 inches. Now the effective cross-sectional area. We have a details button here, and what we can do is either define the outside diameter, the inside diameter. We can also calculate the mean diameter or directly type in the effective cross-sectional area. For me, I'm going to assume the mean diameter is 8 inches and click OK. Our effective cross-sectional area is automatically calculated. We do need to give it a mass of, let's say, 20 pounds, as well as a stiffness, an axial stiffness. For this, we might suggest, or we might get the information from the manufacturer that it's 150 pounds per inch. The pressure force, this is the thrust force due to the internal pressure within this expansion joint. So here is where we will have both options for the start and the end of the expansion joint. We can apply the entire force. We can choose just the bellow, which we can see this graphic update here, or no force at all. For our case, we'll leave this as entire force. Now the flanges, again, once more, I want to apply just our general flange of 16 pounds, 232 psi to both nodes. So now, once I click OK, it'll ask me, do I want to clear my results? That's fine. And here is my expansion joint that was just generated. Now, it's quite common for expansion joints to be added in pairs. It's not so common for them to be added individually. So maybe we want to quickly add a second expansion joint. We'll add that to this new piping member that was created here. Now, everything is the same except for now I want to choose to start at 12 inches from the member end. So flying through this other information, the length will once again be 12 inches. The outside diameter is 10. The corrugated length is 10. And my mean diameter is going to be 8 inches. The mass was given to us by the manufacturers, 20 pounds, with a stiffness of 150 pounds per inch. The flanges, we will apply our 16-pound flanges, 232 psi to both nodes and click OK. So now we have our second expansion joint added here. So what we'd like to do is to rerun those calculations back in our piping module. So right now, as I mentioned, our drop-down says that we're in RF piping design. I can always go to my add-on modules and go to my current module because that's currently selected. So we'll rerun our calculation here. And again, this is cycling through the load cases combinations, now with those expansion joints added. So now we can see here that the overall code check was decreased significantly. So by adding in those expansion joints, we've now decreased the stresses in those bends. Keep in mind, if I make any changes to the cross-section or the design pressure temperatures of my cross-sections, I probably want to go back and double check this internal pressure analysis to make sure that everything is checked for here. These are two separate checks. One additional thing I want to point out that I think is really strong with our program versus others is that you'll notice for all of these checks, we give you all these code references along with the variables. So for example, if we're looking at one of these expansion checks, you can see in our additional information down here, we have all of the variables that went into play along with the code references for those variables and how they're calculated. Remember stress intensification factors, things like that. The design formula is even given down here according to section 104.8.3 equation 17. We can even expand some of these trees here to get our design internal forces, cross-section properties. So we want to be very, very clear to you as a user where your numbers are coming from rather than being a black box. You can always export all this design information back into Microsoft Excel for further sorting as well. So pretty powerful in terms of our data output. So now we are done with the piping design. The last couple things I want to touch on, number one, is the design of our supporting structure here. So the supporting structure, we can further add in loads. Remember I mentioned that we have dead loads, live loads, snow loads. We can add all those loads to our supporting steel members here, create load combinations, and we can go into one of our add-on modules called RF Steel AISC. Now this add-on module looks identical to what we were just using with the piping members too. So again, once you learn one module, a lot of the modules are set up the same. So then we could design according to the AISC 2016 standard if we choose to do so. Point being that you can design both the supporting structure and the piping members all within one model, so you can take into account that interaction. So I do have further webinars that go into much more detail on only steel design, for example, and you can find those on our YouTube channel or on our website, so I won't have time to get into that today. Now, lastly, I want to touch on our printout report. So let's assume, for example, we have these loads, remember, that we've applied to our piping members, and we'd like to quickly add a picture of this to our printout report. We're ready, we've done the design, we're ready to submit these for review. Well, we have this nice feature up here to print a graphic. Now, typically with print a graphic, you would have to individually change your load case, print it off, come back in Rfem, change it, print, and so forth. We have this option called mass print. Under mass print, the program has already populated what I'm currently looking at, assuming that I'm wanting to print off this. Now with mass print, what I can do is to select to print off all load cases and combinations. So I'm going to get a view of all those different loads printed off at once. I'm going to use 50% of the page height. That's great. I click OK. Now the program's saying, okay, well, you haven't created a printout report yet, so let's set up a template. So I click OK with that. Now the program will automatically jump into an additional application here that shows our printout report. So with the printout report, we have our table of contents over here on the left, and there are our pictures that we just printed off. They're allocated into the correct location, so they're automatically put into this section loads, and now I can scroll down through. I can see my pipe fluid added here along with my table, temperature 1, temperature 2, and so forth. And if I ever decide, I don't really love, the view of this particular picture, I can always right-click to edit it. And maybe I want to zoom in here to just this section that I'm most concerned with. I click back. Now this printout report, and in particular that picture, will automatically be updated to show that new view. Something else that's extremely powerful is that these pictures are all synced up to our current RFEM module or our current RFEM file. So if I were to go back into RFEM and make any changes to these loads now, the pictures will automatically be updated when I come back into the printout report, so I don't have to worry about reprinting those. And as you can see, we have all of our input data for our supporting structure from RFEM, which would be our pipe rack, and then we have our input data for our piping system, including RF piping design. So if we scroll down here to RF piping design, remember I had shared with you, oh, well, we give you all the code references, all the variables, all the design internal forces. Not all of that has to be printed out. You can see here that it's nice and short and sweet. We give you the controlling code reference, the controlling ratio, and that's really it. But if you want to add any more information, maybe this isn't complete enough for you, under Edit, Selection, for example, here's both RFEM and RFEM piping design. This is where you can uncheck and check boxes all day long to make it catered to what you want to include in your printout report. You can also save templates and use those templates on for additional files, including adjusting your header and your own logo. So quite powerful when it comes to our printout report as well. Okay, so that concludes our webinar today. So I will continue on with our PowerPoint. That was, of course, so much information within the last hour. You can always find more information on our website at Dlubal.com. We have many social media sites that will be helpful as well. In particular, I mentioned our YouTube channel. This has all of our previously recorded webinars, such as this one, available for you to watch for free as well. Now, our email for our Philadelphia office is info-us@Dlubal.com. Our phone number is 267-702-2815 if you have any questions or comments about today's webinar, or anything else for that matter. Now, we will have many more upcoming webinars. You can register on our website at Dlubal.com under Support and Learning and Webinars. As most of you know, because you're here today, that I sent out a couple reminder emails as well. So keep an eye out for that. Now, many of you are wanting PDH credit for today's presentation. That's great. I just ask that you please send me a request through email to info@Dlubal.com. Again, that's info-us@Dlubal.com. I please request that you were available for the full hour-long presentation, and let me know who all was in attendance if there was other people besides yourself. And with that said, I want to thank everyone for attending today, and as always, I hope to see you at our next webinar. Thank you.